All right, good afternoon, lads and ladies. Welcome back to Calc 2. Today we are going to dig into section 7.3 on trigonometric substitutions. So put on your brave pants and fasten your helmets and let's get to this. I'm gonna close my door here real quick. And we can get moving. So at the end of class last time, we discussed a little bit what trig sub is and why it is useful. We saw one particular example of an integral that could be solved using purely geometric means. But if we wanted to find an antiderivative, we would have been in trouble. So today we're going to go a little bit more broad. Let's get into it. So this is MAC2312 section 004. We're doing a lecture and the date is the 2nd of February, 2021. Today.
Professor, I had a quick question.
Yeah.
On the homework, it's one of the problems. So later on, if we can work it out.
Sure. So
it's with trig functions.
Section 7.3 on trig sub. Yeah, we can take a homework question at the start.
I think the just WebAssign wasn't taking the right answer because I did it like 3 multiple ways. I even used math ways and it just wasn't taking anything. So I don't know. I just wanted to see what was happening.
Okay. Yeah, so what is the homework question? Where did it come from?
I have it right here if you want me to just say it.
Sure.
It was actually integral of 9 tangent to the 5th x dx.
Okay. And for everybody else's purposes, do you remember what problem this was?
Yeah, 12 on homework 4.
All right. So first we're going to pop out the 9, and then we need to integrate the 5th power of tangent. I think we may have done this one in class, but the key here is to try to make an appropriate substitution, right? So this isn't trig sub, this is a 7.2 question, but we're going to attempt to solve this by making a substitution. Normally, if the power of tangent is odd, then we will try to sub for secant, right? That is our usual goal here. We grab off a secant tangent and then try to substitute for secant, but there isn't a secant for me to grab off here. So that's a challenge. I might start by writing this as 9 integral tan to the 4x times tan x dx. And then I'll start expanding this 4th power of tangent in terms of secants to see what I can get. So that's the same as 9 times the integral of tan squared x all squared times tan x dx, which is 9 times the integral of secant squared x minus 1 all squared times tan x dx. And now I'll FOIL out that secant squared minus 1 all squared. That's secant to the 4th of x minus 2 secant squared of x minus 1 times tan x dx. And so really what I'm looking at here is 3 different integrals. I'm going to distribute this tangent back through, and I'll consider how to do secant to the 4 times tangent, separate from how to do secant squared times tangent, separate from how to do 1 times tangent. And I think maybe if we're clever, we can get away with doing this as 2 integrals, but everybody with me so far?
Yep.
All right, so far just a trig identity, right? Just a little bit of algebra and 1 trig identity. Now I'm gonna distribute the tangent back through here, and I'll do it like this. I'll call this secant to the 4x minus 2 secant squared x times tangent x minus tangent times 1 is just tan x. And then close bracket and then dx. Because my intent, looking at each of these pieces, in each of these I'll have an even power of secant, which is kind of nice because then I could substitute for tangent. And then in this one, I'm gonna have to handle things totally differently. So I'll split this now as 9 integral secant to the 4th x minus 2 secant squared x times tan x dx minus 9 integral tan x dx. Now the integral of tangent, this piece I know how to solve. This is the natural log of secant, right? Or negative natural log of cosine. This is one of my fundamental trig integrals. This fellow requires a little bit more love. What I would do in here is I've got like secant to the 4 times tangent and secant squared times tangent. I'm gonna grab out a secant squared and distribute the tangent back in. So this will become secant squared x minus 2 times tan x times secant squared x dx minus 9 integral tan x dx. And then in here, what I'm thinking is in this first integral, I'm going to substitute for tangent because I can use this secant squared here to do that. And the secant squared that's here, I can rewrite in terms of tangent. Secant squared is the same as 1 plus tan squared. So what I'll get here is 9 integral parentheses. Secant squared is 1 plus tangent 1 plus tangent squared x minus 2 times tan x times secant squared x dx. And then this guy's still hanging on here like this. It's about to fall. So I can combine like terms here. I've got a +1 and a -2. This is the same as 9 times tan squared x minus 1 times tan x times secant squared x. And then over here, I still have minus 9 integral tan x dx. In the first integral, I'll substitute z equals tangent. Z equals tangent x. dz is then secant squared x dx. Over here, this 9 integral tangent, this is the same as 9 integral sine x over cos x dx. So in this one, I would substitute like w equals cos x, dw is negative sine x dx. Really, the integral of tangent is one that we should just know. Right? We shouldn't really have to work this out. But in case you forgot where that comes from, this is where that comes from. So altogether here, I'm going to have 9 integral z squared minus 1 times z dz that's that first integral, minus 9 integral sine x dx is negative dw, so I'll have negative 1 over w dw here. This negative can pop out and make this a plus. In the first integral, I can distribute, so I'll have z cubed minus z dz plus 9 integral 1 over w dw like this. the first integral is a polynomial. The second one is a natural log thing. So this will become, let me just zoom out a little bit. So this guy is going to become 9 times z to the 4 over 4 minus z squared over 2 plus 9 times the natural log of the absolute value of w, and I'll slap my plus c on. And then we have to chase back through both of those substitutions. So this is 9 bracket, 4th power of tangent over 4 minus 2nd power of tangent over 2 plus 9 times the natural log of the absolute value of cos x plus c. And this should be your answer. You can distribute this 9. And this is what we should get.
If we integrate tangent as ln secant x, it's still correct, right?
So the integral of tangent, there's a few ways to do this. Integral of tangent, you can write it as the negative ln of absolute value of cos x plus c, which is the same as the positive ln absolute value of secant x plus c. Either one is fine. The two negatives combined here to make a positive. So kind of the more natural way to write this one was as the natural log of cosine. No pun intended. But if you wanted to, you could also write this as a minus natural log secant because the minus here.
Yeah, that's exactly what I had. I had 9 tangent to the 4x over 4 minus 9 tangent to the 2x over 2 minus 9 ln secant x plus c. Is that correct?
Did you put the secant in absolute values?
Yeah, and it's still marked it wrong.
You know what might be wrong? Like maybe was the variable x or was it like theta or something like that?
Yeah.
No, it was x.
Well, take a screenshot and send it to me. I'll deal with it. If there is some sort of glitch going on there, I would expect other people to run into it. So there's maybe some typographical issue, but we'll see. Take a screenshot, send it to me, and I'll make sure you get credit for the work that you did.
Yeah, it's just I was losing my mind because there was no correct answer.
Yeah, I get how that would be frustrating. WebAssign can sometimes be a little bit dumb, but usually it's pretty good at this stuff. So I'll be a little surprised if there isn't like a typo or something in there somewhere, but if there really isn't, then I'll have to make a correction. And those sort of things, I haven't seen one in a few years in WebAssign, but every now and then I run into them and we have to send a note off to the publisher and get it fixed. So there is a possibility that there's an issue there that needs to be fixed, but send me the screenshot and we'll go from there. All right. So the meat of today is going to be on Trig Sub, which is section 7.3. And the basic idea is we want to transform integrals of algebraic functions which in general are kind of hard, into integrals of trig functions, which are in general kind of easy. By algebraic functions, I don't mean like polynomials. Of course, polynomials are very simple to integrate. I mean like square roots of polynomials, that sort of thing, right? So algebraic allows for more than just polynomial and powers. We're also considering here like all of those combinations together with radical statements. So yeah, the key to all of this, key tool is the Pythagorean identities. Right, so we know that sine squared theta plus cos squared theta is equal to 1, which means that 1 minus sine squared theta is the same as cos squared theta. And similarly, tan squared theta plus 1 equals secant squared theta, which, you know, I would just, honestly, we can just leave it as it is. And then also, we can say 1 minus secant squared theta, that's equal to tan squared theta. So these are useful for getting rid of square roots because they take a difference of two terms or a sum of two terms and rewrite them as the square of something else. So I gave you that little Trig Sub table, right? Or the Trig Sub Bible. This tells you everything you need to know about Trig Sub. If your integral contains a square root of like some number squared minus x squared, then you'll want to make the substitution x equals, in this case, a sine theta, because if x is a sine theta, then the square root of a squared minus x squared will simplify to the square root of a squared times 1 minus sine squared theta, which is the square root of a squared cos squared theta. And the square root of a squared cos squared theta is a cos theta. And there's a similar thing for two other sort of forms. If your integral contains a square root of a squared plus x squared, then you'll want to substitute x equals a times the tangent of theta, because under that substitution, your root a squared plus x squared will become the root of a squared times 1 plus tan squared theta, which will simplify to just a secant theta. I'm not going to write the extra step here. And then lastly, if you have square root of like x squared minus a squared, and you substitute x equals a times the secant of theta, that's nice because then, according to the Pythagorean identity, x squared minus a squared under your root will become the square root of a squared times secant squared minus 1 which will just simplify to a times the tangent of theta. So this is sort of each substitution we make, right? We either substitute for sine, tangent, or secant, depending on the thing that's in my integral. Now, it's not all 100% the case that these are the only times you'll substitute this, and it's not 100% the case that these are the only substitutions that will work. Sometimes you'll have integrals with shit like this that you can do with u sub. And sometimes you'll have integrals without the square root, but like an a squared plus x squared, where you still want to make this substitution. But this is a good general guideline. If your integral has one of these looking square roots, you'll probably want to make one of these substitutions. You should try other methods first. If there's anything easier that will get the job done, like a simple u sub, by all means do that. But if there isn't, then you should follow this guideline. So I'll give you a second to write this down. Your book has a similar version of this table in here. Most people really just memorize the first two columns. These are the get shit done columns. And then these are the why do we do it things. But these are the parts that you must remember.
Does this still work if A has a coefficient that's not -1 or that's not 1?
Right, exactly. Yeah. So I could have like 3 minus x squared under my
Right.
radical, and then I would substitute x equals √3 sine theta.
But if it was like -4x squared.
Oh, if the coefficient of x here isn't 1, you can always force factor that out, right? So if I had 1 minus 4x squared, I could force factor the 4 out, and I'd have 1/4 minus x squared, and that would work okay. So I'll look at an example or two like that, but to warm up, again, let's just look here, because all the others can be reduced to these just through some clever algebra. A note, these are backwards substitutions. In the sense that my new variable, normally when we make a substitution, it's like new variable equals f of old variable. But now it's old variable is equal to some function of my new variable, right? X is the original variable, and theta is the new variable. It's trapped on the inside. This makes the differentials easier to work with. That's one of the big advantages here. So when you do a u sub, you have to like find your du or your dz floating around in the integral. Here you don't need to do that, but you do need to plug in for dx. So this, which makes differentials easier to deal with. But don't forget the differentials. Don't forget to replace dx with d theta and associated pieces. So I'll show you exactly what I mean. We did one of these the other day. We'll do a bunch more today. Let me pull up the textbooks. We have a wealth of examples at our fingertips. The classic example we did the other day is the area of the circle. Let's do this one. What does that lead to? Is this boring? Ah, fine. All right. So I want to integrate the square root of 9 minus x squared all divided by, what is this, x squared? Yeah, x squared. So I look at my Trig Sub Bible, and I notice that this integral contains a square root from my Trig Sub Bible. I look at this a little more closely and ask, could I do this with u substitution? If I sub for the thing under the root, 9 minus x squared, do I have the necessary piece for the differential? Do I have a 2x that I can group with my dx? And the answer is no, right? I don't have an x upstairs that I can group with my dx to make a u sub work here. So the move is going to be a trig sub. I'm going to let x be equal to, this is a squared. So if a squared is 9, a is 3. So I let x equal 3 sine theta. I calculate dx, which is going to be 3 cos theta d theta. since this is an indefinite integral, I don't need to change my bounds, but I'm going to leave some space over here to do something geometric. I'll do that later for this problem, but in the future, I'm going to do that right away, and you'll see why. But for now, this is what I need to make my substitution go. So just leave yourself some space here. In my integral, everywhere there's an x, I'm going to write 3 sine theta instead. So upstairs, I'll have the square root of 9 minus parentheses 3 sine theta all squared. And downstairs, I have x squared, which is, God damn this pen, parentheses 3 sine theta all squared. And then dx, this is very important. Don't forget to replace dx by what it is. It's 3 cos theta d theta. All right, so I just replace every piece with its theta counterpart. Every x becomes 3 sine theta, and dx becomes 3 cos theta d theta. The magic happens upstairs with the square root. That's really the point of these substitutions, is to get rid of square roots. So under my root, I'll have 9 minus 9 sine squared theta. Downstairs here, I'll have 9 sine squared theta. And over here, I still have 3 cos theta d theta, like this. I should turn off that heat. Sorry, give me 1 second. Yeah, it's warm outside. There's no reason for us to have the heat on. All right, whatever. So I can't cancel anything here, right? Because this 9 is not under a square root. Everything up here is. You need to factor to cancel anyway. You don't want to do that. What you do want to do is under that square root, factor a 9. So if I factor a 9 out, then that first 9 will become a 1, and the 9 sine squared theta will become just sine squared theta. So this is what I get under my root when I factor that 9. Downstairs, everything else, I just leave it alone. 9 sine squared theta, 3 cos theta, d theta. We'll just wait and figure out the root. Then we'll worry about the constants. 1 minus sine squared, that's cos squared. So under my root is 9 cos squared theta. And the miracle of all this is that now there is no more addition or subtraction under my root. I was able to get rid of the addition and subtraction using this Pythagorean identity. Downstairs is 9 sine squared theta, and over here is 3 cos theta d theta still hanging out. Square roots hate subtraction and addition, but they love multiplication. So now I can take the square root of the 9 and the square root of cos squared, and I get 3 cos theta upstairs. Downstairs, I have 9 sine squared theta, and over here I have 3 cos theta d theta. If you multiply these, you get 9 cos squared over 9 sine squared, right? 9 cos.
We can't bring the constants out?
We can, but they're actually going to cancel here, so I'm not even going to bother. I'm just going to cancel them, right? Cancel, cancel. So this is why I wait till this step to worry about bringing out any constants, because they'll often interact with one another. From here, I'm going to continue over here. Cos squared over sine squared is cotangent squared. Does anybody know how to integrate cotangent squared or just tangent squared? the same trick for both. They're kind of weird.
Would you have to convert it to 1 plus cosecant square first?
Yeah, that's something like that. That's the game. So we use the Pythagorean identity. Cotangent squared plus 1 is cosecant squared. So this is the same as cosecant squared theta minus 1. And then cosecant integrates to negative cosecant squared integrates to negative cotangent. And the 1 just integrates to theta. So at this point, we've solved our integral.
Have we though? Because don't we need to resubstitute back to x?
Yeah, you're one step ahead of me. So there is no more integral, but if I asked you this problem and you gave me this answer, I would be like, what the fuck is theta? What are you talking about? I asked you about oranges and you're talking about unicorns. So how do we go from the unicorns back to the oranges? That's why I left some space up here. So in the spot where I would normally change my bounds, if I'm doing an indefinite integral using trig sub, that's where I like to draw a little triangle. I'm going to take some extra space to do this here. Since x is equal to 3 sine theta, that means x over 3 is equal to sine theta. And you know that sine theta is the opposite over the hypotenuse, right? That's SOHCAHTOA, yeah, hypotenuse. So I can come in here and draw a little triangle where one of these angles is theta, and then use my substitution to complete the triangle. I'll draw the opposite side as x and the hypotenuse as 3. And this is always a right triangle that we draw. So I can figure out the missing side using Pythagoras. If this squared plus this squared equals this squared, then this guy is the square root of this squared minus this squared. So this missing side is the square root of 9 minus x squared. And that's what I put in my little substitution box for these. Why is that useful? Well, because I've got down here cotangent of theta, and I need to know how to write that in terms of x. This triangle is the key to going back and forth from x's to thetas. So if I want to know what is the cotangent of theta, remember that cotangent, that's the reciprocal of tangent. Tangent is the opposite over the adjacent. So this is the adjacent over the opposite. So cotangent of theta is the square root of 9 minus x squared over x, the adjacent over the opposite. So down here, negative cotangent theta is negative square root 9 minus x squared over x. And then I still have this minus theta plus c. What about the theta? There's a handful of ways to write this, but we know that the substitution I made was sine theta equals x over 3. So I can solve for theta here by taking the inverse sine. So theta is the inverse sine of x over 3. And we put all that together, we get negative square root 9 minus x squared over x minus the inverse sine of x over 3 plus a constant. And that's your final answer here. Yeah, very good, Matt. So the trig integrals themselves, you have to do a fair bit of careful simplification to get your algebraic integral down to a straight up trig integral. That requires being good with your trig identities, careful with your square roots, careful with all your algebra and multiplication. Then you do whatever you need to do to solve this trig integral. It's going to be a 7-2 integral. It's going to be an integral just like the ones we were doing last week. You do whatever you need to do to solve that integral. And then you've got a meaningful trigonometry problem to go from this answer back to this answer. The answers to these trig integrals are always either trig functions themselves, for which you'll use your triangle, or theta, powers of theta, that kind of thing. And these you will always get just by solving your original substitution for theta. So you may remember in your trig class where you were told, you know, x equals 5 sine theta, rewrite cotangent theta in terms of x, right? Where you had to go from an expression like this to an expression like this. This is the reason for that, right? The reason we have you guys do that in trig is precisely so you, when you get to these problems, you know how to handle them. So I'll give you a second. Make sure your notes are nice and clear. If there's any part of the page you want to see, let me know. I'll move it around, zoom in, whatever.
Before we move on, would it be okay for you to explain how you went from x to theta or theta to x slowly for those of us who have trouble understanding it? Because I see the triangle that you drew, but I'm a little unsure as to how you got from sine theta equals x over 3 to square root of 9 minus x squared over x.
So it's all about the triangle, yeah. So let's come back here. Normally I do this right away after I make this substitution. As soon as I make the substitution, I draw the triangle. So the substitution was x equals 3 sine theta. I know I want to draw a triangle, so I'm going to get sine theta alone because I have a geometric interpretation for that. To get sine theta alone, I divide both sides by 3, and that gets me here.
Okay.
Now from here, I remember SOHCAHTOA, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I've got sine theta equals some fraction. So I can think of the top as the opposite and the bottom as the hypotenuse, because sine is supposed to be opposite over hypotenuse. That's my SOHCAHTOA. So then I draw a right triangle with one of the sides or one of the angles here labeled as theta. And I know that my opposite side length, this guy, should be x because opposite is x. And I know that this side, my hypotenuse, should be 3 because downstairs I have a 3. So then I have this triangle with the 3 and the x labeled, but I don't know the bottom yet. I don't know the adjacent side. But if you have a right triangle and you know 2 of the sides, you can figure out the missing side using a squared plus b squared equals c squared. And that's where I got the square root of 9 minus x squared here. If you want to label this as b and then like solve for it, that's fine. But we want to get comfy and quick. A useful trick is that the missing piece of your triangle is pretty much always going to be the thing that you're trying to get rid of in your integral. So the piece that I had to solve for here, I could have been even lazier and said, well, I know the way Trig Sub works. This is pretty much always going to be this. That's not always true, so I don't recommend you think of it that way. I recommend you think of it as using Pythagoras to solve the triangle. But you'll find in 9 out of 10 problems that this piece is the square root you're trying to get to go away. Does that make sense? Feel better?
Sort of. It's going to take a little bit.
It will.
We'll
This is hard. I don't expect anybody to feel like wonderful about this right away. But are there any places here where we want more details, more notes, just more time to look and write?
Oh, sorry, you can go.
Yeah, never mind. Sorry.
I was gonna say like, is there any other way to do it? Because I was looking at this one video and they were saying that there's like an algebraic way to do it as well. Or like, should we just learn how to do it with the triangle?
An algebraic way to do what?
Like to get like, you know how you got like cotangent of theta is not square root of 9 minus x squared over x. Like, I don't know, maybe I'm remembering wrong, but they said there was like an algebraic way to do it.
Yeah, you really want to use the triangle here. So here, we'll
Okay.
do this off to the side. If you wanted to, here's an alternate approach. You know that sine squared theta plus cos squared theta is always 1, right?
Yeah.
And if sine is x over 3, then sine squared theta is x over 3 squared. So you can plug that in to get this. I don't recommend writing this down, just to be clear. This is x squared over 9 plus cos squared theta equals 1, which means cos squared theta is 1 minus x squared over 9. So cos squared theta common denominator is 9 minus x squared over 9, which means cos theta is the square root of 9 minus x squared over 9, which is the square root of 9 minus x squared, like that, over 3. And once you know sine, which we started out knowing, once you know sine and cosine, you can build all the other trig functions out of them. But for my money, there's way more room to make mistakes here than there is drawing a triangle. So I strongly recommend you do this by drawing the triangle. Not only is this kind of a pain in the ass, but it just gives you sine and cosine. If you want cotangent, you would then have to divide cosine by sine and be very careful managing the fractions. Whereas if you want cotangent from the triangle, you just go, oh, it's adjacent over hypotenuse, boom over boom. You don't have to worry about canceling fractions. So yes, there are ways to avoid the geometry if you are desperately allergic to it. But unless you literally go into anaphylactic shock every time you draw a triangle, I strongly encourage drawing the triangles.
Okay, thank you.
I'm going to do a very tame example next, a very gentle example, to see if we can kind of think our way through it, and then I'll do another more challenging one. This problem we just did is about test level, right? Most of my exam trig sub questions are about this level of difficulty. What follows is a little bit easier than something I would put on an exam, but I think it's a good problem to kind of warm up with. It's also a problem that you've seen before. I bet at least half the class remembers this integral. What is this?
That's the inverse of trig, or
Inverse
tangent,
tan?
sorry.
Yeah.
Yeah, arctan, right? Inverse tangent. Sorry, my camera's fucking up. Arctan. Yep, this is arctan x. The proof that this is arctan x is usually done by figuring out the derivative of arctan and then saying, oh, well, this, I know 1 over 1 plus x squared is the derivative of arctan. But you can also cook this up using trig sub. There's no square root down here, but pretend that there was. Then I would substitute x equals the square root of 1 times tan theta. So the square root of 1 is 1. So I can do this by substituting x equals tangent theta. Dx is secant squared theta d theta. And if I'm being good here, I should draw my triangle. Now I know that tan theta is x over 1, right? Because x, you know, there's just a 1 here. And I can think of this as my opposite and this as my adjacent. So, okay, the opposite side is x, the adjacent side is 1, and that makes my hypotenuse square root of 1 plus x squared. So there's our triangle. It's a right triangle like this. Now, if I go plugging these things in, I'll have 1 over 1 plus x squared is tangent of theta all squared times dx is secant squared theta d theta. So that's secant squared theta over 1 plus tangent squared theta d theta. 1 plus tangent squared, though, that is secant squared. This is secant squared theta over secant squared theta d theta. Those cancel. And I'm just left with the integral of 1 d theta. The integral of 1 d theta is just theta plus a constant. And since tan theta is equal to x, I can see that theta is the inverse tangent of x. So this is inverse tangent of x plus c. And I didn't actually need my triangle for this because I didn't get any trig functions in my answer. I just had theta itself. But if I'd gotten any other trig functions, I would go back to x's using this triangle. So this is another way to get the integral of arctan, right? The integral of 1 over 1 plus x squared as arctan. And there's a generalization of this integral that's really good for you guys to work out. So a homework problem I'm going to leave to you guys. It's not in the homework set, it's not in the book, but it's one that you should do. I'll hold here just for a minute for those who are writing. Is what happens if I change this 1 to a 2, or to a 5, or to any number a squared? So moving up now, a problem for you to solve. Prove that the integral of 1 over a squared plus x squared dx is always going to come out to 1 over a times the inverse tangent of x over a plus c by substituting x equals a times the tangent of theta and dx equals a secant squared theta d theta in the above integral. This integral I actually consider as fundamental, right? It's in the table. If you look back at your table of basic antiderivatives from section 4.10 or section 5.4, this is in there. And it's one that you guys should know. And you should prove it, right? If you want to remember something, the best way to remember it is to prove that it's true. So run through this problem. It's just like the one we did up here. It's the exact same thing, and you'll get secant squareds canceling, but instead of a 1 here, you'll have a 1 over a. And then when you go back to your x's, you'll end up with the inverse tangent of x over a for theta. The integrals for the inverse sine function and inverse cosine function, like 1 over the square root of 1 minus x squared, they all go the same way. All right, so I'm going to zoom out a little bit in case anybody wanted details from the problem above. We'll try to get your problem in here too.
How do we know what to substitute for x?
That's the Trig Sub Bible, right? So that was the thing we started with. If your integral contains, make this substitution. So I can bring that back. If your integral contains one of these things, you will substitute one of these things.
Even if it doesn't have the square root, like for example, that problem you just showed us, like 1 over a squared plus x squared, since we see that's
Yeah, so this is a guideline for 99.9% of problems. Just like LIPET works 99% of IBP problems, there are exceptions. And that one I just showed you is one of the very few exceptions to the rule. So most of the time, this will save your booty. But if you're working a problem that you can't solve with U sub, you can't solve with integration by parts, and you think you might want to try Trig Sub, even if it doesn't contain one of these things, give it a shot. Keep in mind just what makes this work, right? Why is this useful? Because it takes a sum or a difference, like a squared minus x squared or a squared plus x squared, and turns it into a single term. So anytime that sort of transformation is useful, these substitutions can be useful. If we look at the integral we were just doing, what makes this integral hard at the outset, I mean, if you don't know a priori that this is arctan, what makes this integral hard is that downstairs you have a sum of two terms. Fractions don't split up over their bottom, right? Like I can split up a fraction like a plus b over c as a over c plus b over c. This shit works fine. But a over b plus c, that does not split up as a over b plus a over c or anything like that. So anytime you have a sum or difference of two terms in a place where you would much rather just have a single term, these sort of substitutions can be useful. Certainly, under square roots, we want to get rid of sums and differences because square roots hate addition and subtraction. But also, in general, downstairs in fractions, right? Fractions don't really play nice with addition and subtraction in their denominators. So if I can get rid of this plus and turn this into a product or just a single term, which is exactly what this substitution does, right? From here to here, I go from having a sum of two terms downstairs to having a single term downstairs. That's a good step, right? Trying to get nice denominators that don't have addition or subtraction, that don't have square roots. Those in general are the types of things we want to clean up. And this substitution helps with that regardless of whether there's a square root or not. But that's sort of the short answer. The long answer here is fucking depends, man. It really depends on the problem. Some problems yield really nicely to these things, even if they don't look like they will at first. Some problems look like they'll yield nicely to these things, but end up not coming out so nice. So really, it's like cooking. How do you know to put thyme on top of a steak? Well, you've seen it done before and it smelled nice when you went to that restaurant. So let's give it a try. And, maybe it comes out good with the seasonings you chose. Maybe it doesn't. It really depends. And it's going to be something that you'll get better at the more you practice. So you kind of develop a nose for this stuff. All right. Let's try some more problems.
Can I ask a question before you move on?
Sure.
If this problem was 1 over 1 minus x squared, would you just sub for sine and do the same thing?
We could do that. That's an option. But 1 over 1 minus x squared also has another way to solve. And that's something called partial fractions that we'll look at soon.
But it does work with subbing for sine.
It will. Yep. You can do that one with Trig Sub. It'll work. But let's try something a little more typical of what we'll see here. Is that squared? Yeah. What you'll see is you kind of have to pick these problems carefully to avoid secant cubed. Secant cubed just likes to show up in these problems, which is why I kind of rag on it hard in IBP. So I'm choosing our example problems here really carefully because I don't want to give us a really frightening trig integral, at least not at first. But if I look at this and I compare to my Trig Sub Bible, I have an x squared plus 4, which is like a squared plus x squared. So the move here is going to be to substitute x equals 2 times the tangent of theta, which will make dx 2 secant squared theta d theta. Now, if x is 2 tan theta, then tan theta is x over 2. So I'll think of this as my opposite, and this is my adjacent. And I'll draw my triangle. My opposite side length here is x. My adjacent side length here is 2. Then this guy has to be the sum of the squares of this guy under a root. So this guy is going to be x squared plus 4 under the radical. And that's my little trig sub box. And when I implement the substitution, most of the work is downstairs. X squared is going to be 4 tan squared theta. That's just this piece. Then my square root is going to be 4 tan squared theta plus 4. And my differential, which I'll just put upstairs, is 2 secant squared theta d theta.
Why did you add the 2 to the substitution?
So look at that table again, the Trig Sub Bible. If you have a squared plus x squared under your radical, you should substitute x equals a times the tangent of theta. It's so I can factor out this 4 and get a tan squared plus 1. My kind of high level goal is to use the Pythagorean identity tan squared theta plus 1 equals secant squared theta. So I need to make sure whatever number is in front of this is the same as the number here, so I can factor it out and get tan squared plus 1. So the number that goes in front of your trig function is the square root of the constant under the radical. So I had x
Yep,
squared
I see it.
plus 4, so I'll use 2. Now from here, I'll have integral 2 secant squared theta over 4 tan squared theta times radical 4 parentheses tan squared theta plus 1. That's all under my radical, and then I've got a d theta here. And now this tan squared plus 1, that is secant squared. So I'll have integral 2 secant squared theta over 4 tan squared theta times the square root of 4 secant squared theta d theta. And the square root of 4 times secant squared theta is 2 secant theta. So I'll have integral 2 secant squared theta over 4 tan squared theta times 2 secant theta d theta. I've got secant squared times secant squared upstairs there, or sorry, secant times secant upstairs there, that's secant squared. 1 copy of secant down here, so I can cancel one of those. I can also cancel the 2's, and I'll get secant theta over 4 tan squared theta. That 4 is downstairs, so it can pop out as a 1/4. And I always wait till this step because you never know how these constants are going to mesh together. But now that all the constants are taken care of, I'll pop out the 1/4. And then secant theta over tangent squared theta I'll just write it like that for now. I'm gonna rewrite these in terms of sine and cosine and see what I get. That's 1/4 integral parentheses 1 over cos theta divided by parentheses sine squared theta over cos squared theta. And yeah, we'll move up here. This is 1/4 integral. The 1 over cos theta upstairs stays. And I multiply by the reciprocal of this guy, which is cos squared theta over sine squared theta d theta. And you'll see the cosines will interact. So I'll get 1/4 integral cos theta over sine squared theta d theta. And now I've reduced this to a 7.2 problem. So questions so far? All right. How do I solve this integral? Cosine over sine squared.
It's the same as cotangent cosecant.
Yeah, let's see. Yep, I can write that as cosecant cotangent. That's clever. That wasn't even what my brain was wanting to do there, but you're 100% right, and I think that's the faster way to do it. So this is 1 over sine theta times cos theta over sine theta d theta, which is 1/4 integral cosecant theta times cotangent theta d theta. And then whose derivative is cosecant cotangent?
Negative cosecant.
Good, so this is negative 1/4 cosecant theta plus a constant. You could also substitute for sine, right? At this step, if you substitute w equals sine theta, dw is cos theta d theta, and you integrate 1 over w squared to get negative 1 over w, which would be negative 1 over sine, which is cosecant. So either way works great. I think this is fun to stay in trig land, so nice observation. But we do still need to go back to our original variable. So if I zoom out.
Professor, can you
Yes.
explain the last part, please?
Say that again?
Can you explain the last part?
Yeah, so from here to here, I'm just splitting up the fractions, right? I've got sine times sine downstairs and cos times 1 upstairs. So I write that as 1 over sine times cos over sine. And then using the reciprocal identities, 1 over sine theta is cosecant theta. That's the definition of cosecant. Cos theta over sine theta, that is cotangent theta. That's the definition of cotangent. And then we know that the derivative of cosecant is cosecant cotangent, just with a negative. So the integral of cosecant cotangent is negative cosecant.
Okay, sure. Thank you.
So it's a little sneaky. Yeah, it's pretty clever. Again, if you want to try something else, the other option is at this stage, you let z be sine theta, dz would be cos theta d theta, and your integral would turn into the integral of 1 over z squared. and that would be z to the negative 2, who integrates to negative z to the negative 1. So you'd end up with negative 1 over sine theta, which is negative cosecant theta. Either one is fine. But no matter how you get there, you're going to get to this, or you're going to get to something like 1 over sine theta. So you need to come back to your triangle. I need cosecant theta, which I know is the reciprocal of sine. Sine is the opposite over the hypotenuse, so cosecant is the hypotenuse over the opposite, which is the square root of x squared plus 4 over x. So we can just read that off from our triangle. So this is negative 1/4 square root of x squared plus 4 over x plus c. Very sneaky, right?
Can I ask a question?
Of course.
Why can't we solve for theta, making it tan inverse of x over 2, and then just make it cosecant of tan inverse of x over 2?
You can, but that has all sorts of domain restrictions. Remember the inverse tangent function, he's only valid for inputs, he's only valid for theta values that run from negative pi over 2 to pi over 2. And those might not be values that correspond to the x values I'm interested in, like if this was a definite integral. Also, cosecant of inverse tangent of x over 2 is just ugly, right, compared to this. So while it's not incorrect to say that this is cosecant of arctan of x over 2, it's certainly not pleasant.
They are equivalent, yeah?
They are equivalent as long as you stay within the appropriate domain. The domain, the set of all x values for which this is a valid function is different than the set of all x values for which negative 1/4 cosecant of inverse tangent of x over 2 is defined. So this also has a larger domain, and everywhere on this thing's domain, it satisfies the original integral. So I would prefer the answer that gives me the largest possible domain. That's one reason we like to go back to the algebraic form. Another reason is that the integral was given as an algebraic function, right? I was asked to find the antiderivative of this algebraic function. So it's nice to have your answer given in the same sort of style as the original problem. But they are equivalent. On a test, though, I'll tell you, I would take off probably a point or a half point for not converting back. If you made no effort to convert back and you just gave me this answer, then I would take off a full point. If your effort to convert back was just swapping theta with arctan of x over 2, that would be at least a half point, maybe a full point, depending on the problem and whether it was a definite integral where we really needed the broader domain or not. So I would encourage you to get comfy with this, right? We have lots of problems like that in trig, like write cosecant of arctan of x as an algebraic function. Again, the reason we include those problems in the trigonometry class is because it's a skill we really do care about here. If you were working, for example, a physics problem that required this integral, you really don't want to tell somebody that the force they're going to work with is the cosecant of the inverse tangent of something, right? It's much nicer to be like, oh yeah, it's the square root of 7. So let's do our best to get back to these nice answers. But it would be valid. It's not incorrect. It's just not ideal. Other questions or comments here? Anything that we would like to look at more closely or discuss more details of? Ethan, I think I can see you talking, but it looks like you're muted still.
Oh, I'm just working out problems to myself.
Okay, all right. Are we all comfy with where this triangle comes from? Okay, how am I doing on time? We're at 1:40 now, so we've got I have you guys 5 more minutes. Let's try to get one more good one in here in 5 minutes. I would like to do a definite integral. These are fun, but they're not definite integrals. Maybe we'll do one of those next time. Example 6 looks properly terrifying. We can do this. Maybe. No, we'll save that for next time. I want a definite integral that isn't quite that fucked up. How about 14? We're gonna have c squared. Yeah, this is not too bad. If you've in your past studied any hyperbolic trig functions, this is a nice problem down here, number 31, showing that the inverse hyperbolic sine function can actually be re-expressed as a logarithm like this, using some formulas that you may have seen in Calc 1 if you studied hyperbolic trig functions. But since most people have not, I'm going to go ahead and do 14 as our last example here. That's the integral from 0 to 1. And Thursday, I'll work some more problems like these in lab. 1 over x squared plus 1 quantity squared dx. So the good news is with a definite integral, you don't need to draw the triangle, but you do need to change your bounds, and changing your bounds here requires knowing your inverse trig. I will require you to change your bounds with trig sub the same way I do with u sub. You must do it. The substitution here is x equals tan theta, which means dx is going to be secant squared theta d theta. And our old bounds were x equals 0 and x equals 1. So when x is equal to 0, I will have 0 equals tan theta, which means the inverse tangent of 0 is equal to theta. What is the inverse tangent of 0? What is this number?
How did you get to the inverse tangent of 0 from the tangent of theta?
So I take x equals tan theta and I plug in x equals 0. That gives me 0 equals tan theta. Then I took the inverse tangent of both sides.
Oh,
Becomes
I see.
inverse tangent 0. The right is the inverse tangent of the tangent of theta. That's just theta.
Okay, I hear you.
The inverse tangent of 0 is 0. So when x is equal to 0, theta is equal to 0. You may want to follow some of those links in the review material on Canvas in the modules to brush up on your inverse trig. It will be really important in this section. When x is equal to 1, we have 1 equals tan theta, which is equivalent to saying the inverse tangent of 1 is equal to theta.
Pi over 2?
Ooh, almost.
Pi over 4.
Pi over 4, yeah, because the tangent of pi over 4 is equal to 1, and pi over 4 is between negative pi over 2 and pi over 2. So my new integral is going to run from 0 to pi over 4. And I will get that new integral by plugging in all of the relevant pieces. So new integral 0 to pi over 4. Dx is secant squared theta d theta.
Do we need to worry about multiples of 2 pi?
Yeah, so again, we really need to make sure we're comfy with the definitions of the inverse tangent function. The inverse tangent of x is equal to theta means that tan theta equals x and negative pi over 2 is less than theta is less than positive pi over 2. So we're looking just at this branch of the tangent function. Remember how the graph of the tangent function is made up of all these branches? We just take the middle branch to define the arctan function. So there's only one theta value that satisfies any one of these expressions. It's the one that comes from negative pi over 2 to pi over 2. So they really are unique. The only thetas that I really take as the inverse tangent of 1 are pi over 4. I'm not interested in 5 pi over 4. I'm not interested in 9 pi over 4, or any of the other solutions to this equation. I just want the one from the principal branch, the one from the negative pi over 2 to pi over 2 branch. So finishing rewriting my integral down here, I'll have tan squared theta plus 1 quantity squared. So this was the definition of inverse tangent. The domain restriction here is important. That's kind of what I was saying earlier about rewriting things as like cosecant of inverse tangent. This built-in domain restriction makes that kind of unpretty. So if I simplify here, tan squared plus 1 is secant squared. So I have secant squared theta over secant squared theta squared d theta, which is secant squared over secant to the 4th. Oops, sorry, this is a pi over 4. I wrote a pi over 2. Pi over 4. So I have secant squared over secant to the 4th, which means I have a secant squared left downstairs. Integral 0 to pi over 4, 1 over secant squared theta d theta. How do we do that? How do we integrate the reciprocal of secant squared?
Cosine?
Yeah, I rewrite it as cosines, right? 1 over secant is cosine, just like 1 over cosine is secant. So this is the integral of cos squared theta d theta, which I do using a half angle identity. That's 1/2 integral 0 to pi over 4, 1 plus cos 2 theta d theta. And then I'll take this up over here. That becomes, the 1/2 comes along for the ride. And then the 1 will integrate to a theta. Cos 2 theta becomes sine 2 theta over 2. And here's the good shit. We don't have to use a triangle. We don't have to go back to x's because we were smart and we changed our bounds. You just plug in these new bounds. So this is 1/2 times pi over 4 plus the sine of 2 times pi over 4 all over 2 minus 0 plus the sine of 2 times 0 all over 2. And everything from the second group is 0, right? The sine of 2 times 0 is 0, sine of 0 is 0, 0 plus 0 over 2 is 0. So everything there is 0. From the first group, I will have some contribution. That's pi over 4 plus the sine of pi over 2. 2 times pi over 4 is pi over 2, all divided by 2. And what is the sine of pi over 2?
1.
Good. So this is pi over 4 plus 1 over 2. And you can distribute if you want. That's pi over 8 plus 1/4. So this is trig sub. It's not too bad, but it really depends on how well you've learned your trigonometry, your trig identities, your inverse trig, all the trig integrals. If you wanted to, you could like never teach this as its own thing. You could just say it's another sort of substitution and include it in with the u sub stuff, but it's kind of done backwards, right? We don't, instead of calling our new variable some function of our old variable, we do it the other way around, which makes it a little weird. And also it's deeply involved with trigonometry. You need to be intimately familiar with these definitions because these domain restrictions are everything here. And you need to know your trig identities. You need to be pretty friggin' buff when it comes to the 7.2 integrals. So my advice, finish 7.2 first. Even if you haven't, like, you know, don't feel pressured to go on to the 7.3 problems until you finish the 7.2 problems. That practice will help a lot. But once you finish those, burn hard on these, work real tough, work real hard on these trig sub problems. The new homework is going to drop today. It's going to have trig sub, and it's also going to have partial fractions. So next time I will show you how to do partial fraction decomposition. And then we'll do a little bit of kind of combined trig sub partial fractions review. And then we'll be ready for exam 1. So watch out for that. The study guide for exam 1 is going to drop on Thursday. And it'll be just a handful of problems, 1 or 2 from each of the sections that's going to be on the test. You should work those, write out your solutions, scan and submit them as soon as possible. That way I can get in there and mark them up for you as though they were test problems, and you can get a really good feel for how I grade these things. All right, I know we've gone over by about 7 minutes. Are there any burning questions before we conclude for the day?
When is the test going to be?
Next Thursday.
Okay, thank you.
Yeah.
And will we be doing a review in class, or will we just learn new content up until the test?
So let me write this down. Exam 1 will be next Thursday. I was going to let you guys choose between doing it in the lab period or doing it in the regular class period. What would you guys prefer? So that's 211.
Maybe just doing it in the lab period, because then we'd have some warm-up time in the class period.
How about this? How about I'll conduct a poll this Thursday to determine between the lab. Think about there are strengths and weaknesses to both. Like Ethan said, if we do it during the lab period, we'll have a little bit of time to talk before the test. But also, if we do it during the lab period, then I'm going to have to teach some new content between now and the test. Can't spend all of that class time just reviewing for the test. So it's up to you guys what you would like to do, whether you'd like to do it in the lab or the class period. Be aware that if you pick the lab period, then some amount of one of these days between now and the actual test will be me talking about new material. If you choose to do it in the class period, then the way this will work is I'll finish the lectures for exam 1 this Thursday. We'll do a review in class next Tuesday, and then we'll do the exam during the class period next Thursday. And then the lab period immediately following that, I'll start introducing new stuff. So it's up to you guys how you want to do it. I'll conduct a poll in our next class, and I'll also post an announcement on Canvas once we have this all sorted out with detailed instructions. Remember, you're going to need your phone with Zoom installed. You're going to need your computer with HonorLock installed to Chrome. And you're going to need some tool for scanning your written work, whether that's an app on your phone. iPhone users can use the Notes app. Android users, I recommend Cam Scanner. It's free, it works well. If you have a physical scanner, obviously that is tip tops, but whatever you want to do, just make sure you have a mechanism for scanning, a mechanism for Zoom, and a mechanism for HonorLock, all capable of running simultaneously. All right, that's where I'm going to leave it for today. We'll talk more about the test next time, along with partial fractions. I hope you guys have a wonderful rest of your afternoon, and I'll see you on.
All right. I'll see you office hour tomorrow, because this is Moon Logic, and I need to get myself out of the calculus hole.
Sounds
But,
good.
have a great day, Professor.
All right, I look forward
Did
to
you
seeing
check your
anybody
emails
else.
from me?
I am making my way through email today. I don't think I've gotten to one from you yet, Cody, but well, let me see. No, yeah, I see it right here. Yeah, I'll get to it in just a bit. All right.
Thank you.
Professor Foster, I was gonna ask if I can get a picture of like the top of the last problem we just did. Like
This guy? Oh, sorry, here.
yeah, I can't see it. Yeah.
Yeah. Here we go. Like that?
Yeah, there you go. All right, thank you.
All right. Anything else, guys? Okay.
Have a great day.
See y'all next time.